So in this class, I will explain how to compute the shape factor of a T section, because T section is also very important in steel design. It is also most widely used section. So this is the T section given. All the dimensions are in millimeters. So T section consists of two portions, flange and vector. So this is the flange portion, this is the vector portion. The dimensions are like this: width of flange is 100 mm, thickness of flange is 10 mm, width of web is 10 mm, depth of web is 150 mm. So to find, as I explained in the last class for triangular section, shape factor is defined as ZC divided by ZE. So elastic section modulus about Z axis divides by plastic section modulus about the Z axis divided by elastic section modulus about Z axis. So elastic section modulus as usual is given by ZEZ is given by IZ divided by Y max, whereas plastic section modulus ZPZ is given by A by 2 into Y1 bar plus Y2 bar. So all these I have explained in the first class lecture. What are all these things? Now, we have to locate two axes here. One is the neutral axis, another is the equal area axis. So, to locate the neutral axis, we have to locate the centroid. So, I am going to take G as the centroid of this T section. So, you know the procedure to find the centroid. So, first I will find out to find ZEZ. So, Z axis is the horizontal axis of the cross section as per the code. So, I need to find the value of IZ, then IZ divided by Y max gives the value of ZEZ. But to find IZ, I need to locate the centroid. So, centroid of that complete T section, let me take the distance of that centroid. So, this is the neutral axis. So, G will be here. Let me locate the centroid from this is 100 mm, this is 10 mm, this is 150 mm, this is 10 mm. So, let me denote this distance of this central axis, neutral axis or the centroidal axis from the top fiber of the top line as y bar. So, as per the formula of centroid, we have learned in mechanics, y bar is given by sigma ai yi divided by sigma ai, where yi is the distance, they are the distance of the simple sections. This T section is split into two rectangular sections. So, you have to look at the centroid of this rectangle and centroid of this web portion. So, there are two portions here. This is the first rectangle, this is the second rectangle. Please note that T section is not symmetrical about the horizontal axis, it is symmetrical about only the vertical axis. So, here what I have to do here is, this is nothing but A1 Y1 plus A2 Y2 divided by A1 plus A2, because these two areas, this area is A1, this rectangle area is A1, this rectangle area is A2. So, this is the formula. So, A1 is here 100 into 10, that is A1, that is 1000 millimeter square. A2 is 150 into 10, that is the area of the web, 1500 millimeter square. Now, here, once you find these A1 and A2, Y1 and Y2, please note that Y1 and Y2, they are the distances of these centroids. This is the first portion, this is the second portion. Y1 is the distance of the first area A1 from this is my reference axis now. From this reference axis, distance to this centroid is Y1. So, which is 5, half of this 10. So, Y1 is 5 mm. Y2 is the centroid, distance of the centroid of this web portion from the same axis. This is the axis of reference, this is the reference axis for locating the centroid. So, from here, if you take this is 10 and centroid will be a distance of 150 by 2, that is 75. 10 plus 75, this is 85. Now substitute these things there and simplify. Y bar will be A1 is 1000 into Y1 is 5 plus A2 is 1500 into 85 by 2 divided by 1000 plus 1500 A1 plus 2. Now if you simplify this, you will get Y bar as 53 mm. So distance of centroid of the B section from the top of plan is 53 mm. You can always find out from this bottom also. So Y1 should measure from the bottom. That's all. So this is Y bar. After getting Y bar, we have to find out IZ. So IZ is moment of inertia of the section, that is T section, about Z axis. About Z axis. For this, we have to use the well-known parallel axis theorem. By using parallel axis theorem of moment of inertia, you can find out IZ. So according to parallel axis theorem, so now I need the distances of these two centroids from this. So that's what I need. Now we have got the value of Y bar as this distance as 53 mm. We got this as 53 mm. Therefore, the distance of this centroid will be from here, it will be 53 minus 5, that is 48 mm. And the distance of this centroid, of this web. So if this is 53, this total is 150 plus 10, 160. 160 minus 53 is 107. So 107 minus 75 is this distance, is it not? So this is 75, half of this 150. 107 minus 75 means it is 25 plus 7, 32. 32 mm is the distance. So for using parallel axis theorem, we need to find the distance of the centroid G from the other two centroids. Now, according to parallel axis theorem, now I need INA. INA is nothing but your IZ. Both are same. So INA and IZ, they are same. So we are using parallel axis theorem now. Parallel axis theorem is used for these two rectangles separately, like this. So for a rectangle above its central axis, the formula for moment of inertia is BDQ by 12. Now if I take this rectangle, B is 100, D is 10. So 100 into 10 cube by 12 plus area is 100 into 10 into distance of the centroid of this from the centroid of this section, which is 48. So square of it. So please note that this is the parallel system. Plus similarly, I have to apply this for the other rectangle also, that is the web rectangle, web portion. BDQ by 12 for the web means 10 is B and 150 is D here. So 10 into 150 cube by 12. BDQ by 12 is the standard formula for the moment of inertia of a rectangle about its centroidal axis. Plus here, area of this is once again 10 into 150 into distance square, which distance 32. So distance of this centroid of this from the neutral axis, so that is 32 square. So this is the moment of inertia about the neutral axis or the ZZ axis. If you simplify this, you will get the value IZ as 666.08 into 10 power 4. 666.08 into 10 power 4 millimeter power. So this is the unit for moment of inertia. Linear dimension to the power 4. Because B is millimeter, D cube is millimeter cube. So millimeter into millimeter cube becomes millimeter power 4. Now once you get INA, now Ymax. I need Ymax also. Ymax is the distance of the farthest fiber from the neutral axis. So the farthest, there are two distances. For the upper fiber it is 53, for the lower fiber it is 107, higher of these two is 107. So y max is 107. So therefore ZEZ will be IZ divided by y max, which is obtained as 666.08 into 10 power 4 divided by 107. So this value will be in millimeter cube, because IZ will be in millimeter power 4, y max will be in millimeter. Divide, you will get in millimeter cube. The value is 62.25 into 10 power 3. 62.25 into 10 power 3 millimeter cube. So this is the value of ZE. So we got the value of elastic section modulus. Now we need to find the plastic section modulus. Second stage, plastic section modulus ZPZ is given by the formula. The formula here A by 2 into y1 bar plus y2 bar. Now the concept here is we have to get the equal area axis. So here centroidal axis is different, equal area axis is different here, because the given the section is not symmetrical about both the axes. It is symmetrical only about the vertical axis, not about the horizontal axis. So these are the dimensions in millimeters. Now I have to locate equal area axis. Equal area axis means whatever area is there above the axis should be equal to area below the axis. So for this I will take this as h. So or x you can take. So this h is unknown. So this becomes 160 minus h. Total is 160. So 160 minus h. Now what I will do here is this area I will take it as A1. This area I will take it as A. So area above the equal area axis A1, area below the equal area axis A2. So we know that A1 should be equal to A2. So A1 consists of two things. One is this rectangle, another is this small rectangle. So here what happens? This value, of course, this value will be I think 150 minus. This will be 150 minus, because total is 160 minus h. In that I have to get this 10. Then this becomes 150 minus h. Now this is 10. This distance, this thickness of the length is 10. Now A1 is the total area of this rectangle and this rectangle. So bigger rectangle it is 100 into 10. Area is 100 into 10. This portion plus this portion area is 150 minus h into 10. This is A1. This should be equal to A2. A2 is this area. This area is h into 10. Cos 10 into h. Now if you simplify this, you will get the value of h. Once you get the value of h, the equal area axis is fixed. So 1000 plus 1500 minus 10h is equal to 10h. That means 20 times h is equal to 2500. Therefore, h is equal to 2500 divided by 20 or 250 divided by 2, 125. So h value is 125. And that means the equal area axis is at the distance of 125 from the base. From the base it is 125. Now once you get the equal area axis, now this formula we have to use. A by 2 into y1 bar plus y2 bar. In this formula, y1 bar is the distance of centroid of this above portion. That is, above portion means it is in form of a T section once again. This is G1 and centroid of this area, this rectangle, this is D2. Please note the difference here. So here also we are taking distance, but here also we are taking distance. So this distance is y1 bar. Distance of this somewhere here it will lie. This distance is y1 bar. Okay. G1 is the centroid of this T section. G2 is the centroid of this rectangular section below the equilibrium axis. This distance becomes. Now we got H as 125. This value we got 125 mm. Definitely this y2 bar will be half of it. Because it's a rectangle. So y2 bar will be definitely half of that. Now I will write here the expression for y2 bar will be definitely half of 125 which is 62.5. So I can directly write here. So y2 bar is equal to 125 divided by 2, 62.5. So only thing is we need to find out this y1 bar. Once again for finding y1 bar we have to consider this T section. Only that portion you have to take. Please observe here. So you make a note of this. Already I told you how to find how to locate centroid of the T section. Here the dimensions are different. 100. This is 10. This is 10. But this value is 150 minus h. 150 minus h means 150 minus 125. That is 25. So this is your equal area axis. Now I have to locate centroid of this one. This T section somewhere here it may lie so that given this distance is y1 bar. Now this is the reference axis now. Equal area axis is the reference axis. So same formula y1 bar is a1 y1 plus a2 y2 divided by a1 plus a2. Here please note that a1 is the area of this rectangle, that is this 100 into 10. A2 is the area of this rectangle, that is 25 into 10. So please note that A1 is 100 into 10 into Y1 is the distance of centroid of this from this G1. Distance of the centroid of this from G1 means it will be how much into this from here, sorry. From here. So from here it is 25 plus 5, 30. Plus A2 here is 10 into 25, area of the red portion, multiplied by distance of centroid of this red portion from this reference axis, which is half of 25, that is 1.5, divided by A1 plus A2, that is 1000, 100 to 10 plus 10 to 25, that is 250. So this is to simplify, you will get the value of y1 bar. I think y1 bar you will get 26.5 mm. 26.5 mm. So it is lying in the web portion only, no problem. So you get y1 bar as 26.5 inch, more than this. That means after finding, you can say that your G1 is here, this becomes your y1. So initially you will not be knowing, after getting that. Now, y2 bar is known, y1 bar is known. You can substitute in the ZPZ formula. So your plastic section modulus ZPZ is equal to a by 2 into y1 bar plus y2 bar. Here, this a is total area of this T section. So total area of this T section, a is given by 100 into 10 plus 10 into 150, which we have got 2500. A1 plus A2. So initially, while finding the centroid, locating centroid, we have found out the 2500. So the answer is now 2500 divided by 2 into y1 bar is 26.5 plus y2 bar is 62.5. Now if you simplify this, you will be getting ZPZ as you will be getting 111250. Please check this. 111250 millimeter cube. Please note that the units of ZPZ and ZEZ, they are millimeter cube. Here y1 bar, y2 bar, they are in millimeters. A is in millimeter square. So if you multiply millimeter square to millimeter, you get millimeter cube. So after getting the ZPZ, now take the ratio of ZPZ to ZEZ. You will get the value of shape factor. The shape factor is always greater than 1 because ZPZ is greater than ZEZ. We can see the values. So therefore, shape factor S is equal to ZPZ divided by ZEZ. So now if you substitute the values, ZPZ is 111,250 divided by ZEZ is 62.2 by 10 power 3 means 62,250. Definitely it is greater than 1, numerator is more than denominator. So the value is 1.787. You can just check that 1.787, which is greater than 1. So this is how we can find the shape factor of a triangular section. So same procedure is adopted to find shape factors of circular section or hollow circular section or a tubular section or an I section, whatever it is. So same procedure. We need to locate the two axes. One is the centroidal axis, that is the neutral axis, and another one is the equal area axis. Centroidal axis is located to find the ZE value, whereas the equal area axis is located to find the ZPZ value. Then take the ratio. Always shape factor is greater than 1.